The synthesis of alkynes, that's going to be the topic of this lesson. And we started this chapter off learning how to name alkynes, learning about the acidity of alkynes, and now we're going to learn how to make alkynes before turning our attention to learning what all the different reactions, that we can do with alkynes for the rest of the chapter. Now, this lesson is part of my new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one or any of my future playlists, subscribe to the channel, click the bell notifications. You'll be notified every time I release a new lesson. All right, so making an alkyne. We're going to find out that making an alkyne has a lot of similarities to making an alkene with one little twist. So in making an alkene, we learned how to do that from an alkyl halide in an elimination reaction. And specifically, we're going to be using E2 elimination reactions exclusively for making alkynes. Now with an alkene, we used either E1 or E2. Here, we're just going to be using E2. Now, as a reminder, let's say we've got this lovely alkene, and if I want to do E2 elimination, I would need a strong base, and we might have used like potassium tertbutoxide, a bulky base, or we might have just used some other strong base like, say, sodium hydroxide, depending on our alkyl halide here in this case. And in this case, we would get an alkene. And in this process, we would actually not only lose the bromine here from one carbon, from an adjacent carbon, we would lose a hydrogen. Might call this dehydrohalogenation. Well, we're going to do the same thing in forming an alkyne, except we're going to have to do it twice. And if we're going to have to do dehydrohalogenation twice, well, then we're going to have two relevant hydrogens and two relevant halogens that we can lose. And this happens in one of a couple different ways. You can have a geminal dihalide. So where you've got two leaving groups, like two bromines is going to be very common on the same carbon. Or you can have what's called a vicinal dihalide, where you've got two adjacent carbons that each have one leaving group, like this vicinal dibromide down here. So those are your options, and we'll find out that we're only going to consider forming terminal alkynes. Now, it turns out it is possible to form an internal alkyne, but it's not commonly presented in many textbooks or courses, so I'm going to not really present it as well. I'll pay its lip service for just a second, but we're going to look at forming just terminal alkynes, and what that really means then is that you need to have your leaving groups either on the very end of the chain or second in from the end of the chain, or one of each, which is what we're considering here. We're also going to learn here that to do elimination twice in a row, you're going to need an even stronger base than normal. And that super duper strong base is the one we just talked about that works for deprotonating a terminal alkyne, and that's going to be sodium amide. We'll find out that's the one we're going to use here. We'll do two successive steps of elimination and one extra thing at the end that'll be related to the acidity we just talked about. All right, so let's take a look at the mechanism just for a second here. So I'm going to redraw this top one here for just a second. So, and the relevant hydrogens will be on the adjacent carbon here. So, and our sodium amide here, it's the amide that's acting as our strong base that's going to allow us to do the E2 reaction here. And we're going to come in and deprotonate a hydrogen. These frees up these electrons to form the pi bond and kicks off a leaving group. All right, so that's going to take us and form us an alkene. We're still going to have one of our bromines left. We're still going to have a hydrogen. So, and it turns out from here, we'll have another equivalent of the amide ion coming in, deprotonating the other adjacent hydrogen, freeing up these electrons to form the triple bond, once again kicking off the leaving group. And it turns out it's the second step that needs the new strong base. This first step of just forming an alkene, we could have done that with like sodium hydroxide or tertbutoxide or something like that. But the second step is going to require an even stronger base than normal to form the alkyne. And we're going to get a little help in the back end from using sodium amide as well, as we'll see. And so in this case, we've now formed our triple bond, and it looks like we formed our product, right? That's the product we predicted every time, except we're not done. We have used excess sodium amide in this case, and there's still sodium amide in our solution. And being a terminal alkyne, we have a hydrogen right here. And let's draw that in black. It's been there the whole time. And amide, we learned, is a strong enough base to deprotonate a terminal alkane in the last lesson. And that's what we're going to do in this step. So we also learned that this effectively goes to completion, and that's important for getting a good yield in this reaction. All right, so we actually formed this acetylide ion right here, and this is key to the reaction here because, again, this step effectively happens 100%. And so if these reactions don't go 100% because this last step does, it effectively pulls everything through from equilibrium there, if you will. So, and it turns out, I mean, these reactions have favorable equilibrium as well, but the fact that this one goes virtually 100% drags them all through. So, and then finally, we'll just add some water in step 2 to protonate this thing and get us our final product. So it's just an acid-base reaction, that last step. But that's why we have to add water at the end, because as soon as you form what looks like your product, it happens in a solution that contains excess sodium amide, and so it immediately gets deprotonated, again, virtually 100%. And that's what the water serves the function of in that separate step, just to re-protonate it. Okay, so there's our 2 successive E2 elimination steps. So we had E2 for the first one, forming an alkene, E2 again, forming an alkyne, and then it immediately gets deprotonated by more sodium amide, only to get reprotonated in step 2 by the water. Cool, and again, this can happen whether you've got a geminal dihalide on the terminal carbon, geminal dihalide on one carbon in, or the 2 terminal carbons each have one good leaving group. It can happen either way. Now, it turns out, if we look at this middle one here, so, well, what if I wanted to form the internal alkyne? Because it turns out that the internal alkyne is actually more stable. So an internal alkyne is actually more stable than a terminal alkyne. So when we actually form this terminal, specifically, we're actually forming a kinetic product. What if I wanted to form this thermodynamic product? Well, it turns out the big reason here is, again, that any of this lovely product you form immediately gets converted into the acetylide ion 100%, dragging it all through. And that's what ends up making this such a favored product. Now, if we wanted to form this internal one, some of you guys might learn that like an alcoholic solution of KOH can pull that off. And so for those of you that need that, great, I just presented it. But for the vast majority of the rest of you, just ignore what I just talked about. Maybe know that there's a way to do internal alkynes that you're probably just never going to learn in your organic chemistry course. Cool, some of you guys will also learn that if you form an alkyne in the middle of a chain somewhere, that it will migrate to the end of the chain in a solution of sodium amide anyways, in what's called the zipper reaction. So I referenced that. I think I even include it on my website, an example of the zipper reaction, stuff like that. But for the vast majority of you, it's not something you're going to need to know either. So the truth is, you can actually do this when your bromines are not on the end carbons and they're further off down the chain, and the triple bond will actually migrate all the way to the end of the chain anyways when possible. But again, most of you aren't going to be presented with that reaction either, once again called the zipper reaction. Now, if you have found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can do to help support the channel. And if you've got questions, feel free to leave them in the comment section below. If you are looking for the study guide that goes with this lesson, or practice problems, or my brand new OChem 1 final exam rapid review, check out my premium course on chadsprep.com.